In this video, I am going to discuss the Sharpe ratio. Sharpe ratio is a comparative measure of portfolios taking account of excess return and risk. So excess return is calculated by RP, the portfolio return, minus RF, the risk-free return, and risk is calculated as the standard deviation of the returns of the portfolio. So the Sharpe ratio is RP minus RF divided by sigma p. The Sharpe ratio is used to compare portfolios with a larger Sharpe ratio, typically meaning that it is a better portfolio. And we can do a couple of thought exercises to understand why. So imagine we have two portfolios which have the same excess return. So RP minus RF is the same for both. But one of those portfolios has a smaller standard deviation. Well, that portfolio is going to have a higher Sharpe ratio. And intuitively, that's a better portfolio. We're getting the same excess return with less risk. Alternatively, we could think about two portfolios that have the same risk, but one has a greater return. Again, the Sharpe ratio of the second portfolio will be bigger than the first, and we would like to choose the portfolio with the highest return for a given amount of risk. Now, so we're going to solve a problem, which is we want to maximize the Sharpe ratio for a portfolio of two stocks. So we want to choose the weights of the two stocks such that we have the largest Sharpe ratio. I have typed the data for our problem into a spreadsheet. So we have returns or expected returns for our two stocks. So the first stock is 6%, the second stock is 8%. We have the standard deviation of those returns. The first stock standard deviation is 20%, the second stock's is 15%, and we have the correlation between those returns. We'll have that at negative 20%. And then finally, we have the risk-free rate is 5%. Now, this is a classic optimization problem. We want to maximize the Sharpe ratio. And so the typical strategy would be to find an equation for the Sharpe ratio using, say, weight 1 as our parameter, and then taking its derivative, finding critical numbers, figuring out whether those critical numbers are maximums or minimums, figuring out which of the critical numbers is associated with the absolute maximum, and that would be the best portfolio. The problem with this approach, or the challenge with this approach, is that this formula is a little bit messy. So I'm going to use Excel to find a shortcut. So let me start by defining the weight of the first stock. We want to know the Sharpe ratio for the portfolio given this weight. Now, I can't calculate it immediately. I need to do some more work. So I need to find the weight of the second stock. That's going to be 1 minus the weight of the first stock. I need to calculate the variance of the first stock and the variance of the second stock. Well, that's just going to be the standard deviations squared. I need the covariance. The covariance is going to be the correlation times the product of the standard deviations. I need to find the expected return. The expected portfolio return is weight 1 times return 1 plus weight 2 times return 2. I need to find the expected variance. That's weight 1 squared times variance 1 plus weight 2 squared times variance 2 plus 2 times weight 1 times weight 2 times covariance. And then, of course, expected standard deviation is the square root of the variance. All of these are calculations. All of these should be formatted as percentages. Now we can calculate the Sharpe ratio. Let's make that an output. The weight 1 should be an input. Again, formatted as a percentage. The Sharpe ratio is going to be the excess return, expected portfolio return minus risk-free, divided by standard deviation. So with a weight of 20%, the Sharpe ratio is 21.91. With a weight of 1%, it's 20.11. With a weight of 50%, it's 17.79, and so on. So we are going to use Excel's solver. So here is our solver. We set the objective to be the Sharpe ratio. We want to maximize the Sharpe ratio, and we want to maximize it by changing the weight of the first stock. And the solver figures out that if we make the weight of the first stock 24.3%, the Sharpe ratio is maximized at 22. Clearly, if we had taken the derivative of the Sharpe ratio, solved for the critical number, we would have found a critical number at 24.3. If we had taken the second derivative of the Sharpe ratio, we would have found that the second derivative was negative, which meant that this was a relative maximum. And if we had looked carefully at our domain, we would have found that this was the only maximum and therefore the absolute maximum. But that would have taken a lot longer. So this is a reasonably good shortcut. We have to be careful in our spreadsheet to calculate the Sharpe ratio, but we clearly can calculate the Sharpe ratio for any given portfolio and then use Excel's solver to find it.